Now this is a particularly important conceptual distinction that you have to understand. That's the difference between populations and samples. So I need to explain how to distinguish between the two, and I need to explain why there's variability between samples, and show that there's more variation between small samples than larger samples. Now, the population is the complete set of individuals that your hypothesis could apply to. So when I was collecting the data from you as students, am I collecting data which is representative of all Westminster students? Is it representative of men and women? Is it representative of everyone in the world? Because those are potential populations it could apply to. But the way you collect your data defines your population. When I'm collecting data about life sciences students, are you like the average Westminster student? Well, probably not, because there's such a strong gender bias in life sciences. There's equally strong gender bias if I was to look in psychology, but if I look at something like engineering and computer science, I wouldn't get the same gender distribution. Now, most of the time, we're not going to collect data about absolutely everyone that we could extend our study to. We're just going to collect a subset, and that's called a sample. So, population, the complete collection of possible items, instances, participants, everything that could ever be done. So a parameter describes the property of a population, and these are represented by Greek letters. So for example, the mean of a population is represented by the Greek for m, which is mu. The standard deviation of a population is represented by the Greek letter s, which is sigma. Now, a statistic is a property of the sample of a population. An example statistic could be the total of that sample. It could be the mean of that sample. It could be the standard deviation of that sample. These are not represented by Greek letters. So a mean is represented by x bar, which has x with the line over the top. And the standard deviation is just represented by the symbol s. So, populations are described by parameters. They're the real underlying values. Populations have means and standard deviations, mu and sigma. Samples have statistics. They are not parameters. They're estimates of the parameter. So as your sample size gets bigger, they get more similar to the population parameters, but they're not in a small sample. So sample means and standard deviations are written as x bar and s. Now, if I'm going to collect data from a sample, how do I get my sample? Are all of the population easy to get? Now, unfortunately, most of the time science does convenience science. So we pick the low-lying fruit. I used to work in protein crystallography. The first things we crystallized were things that we got hold of really easily. Hen egg white lysozyme. It comes out of egg white. It's easy to get hold of. Sperm whale myoglobin. There's loads of it whenever you cut open a sperm whale. These are very easy to get at things, and there's a problem in science that there's a bias to we'll do the easy experiment first. So I was once talking to a statistician who was one of my colleagues at Oxford called Peter Clifford. And Peter had once travelled across America and helping biologists with their statistics. And he met a group of ecologists who were working out in the Midwest of, well, probably a bit further to the west than the Midwest of the United States, so around Utah, where you have the big Monument Valley, where you see in the Wild West films, and you see all these big rock formations and then pretty much wilderness between them. And what they were doing was carrying out the standard ecological investigation using quadrats. So a quadrat is just a square or a rectangle made out of pieces of wood that you drop on the floor, and then you count the number of species, the number of plant types, or whatever you find within that square to do a sampling to see what biodiversity you've got and how many creatures you've got. So Peter Clifford asked them, how do you decide where you're going to drop down your quadrat to make your sample? And they said, well, we drive along, and when we see something interesting, we drop the quadrat. That is not a random sample. That is convenient sampling and you getting the low-lying fruit. You don't want to be analysing that kind of data. But then again, sometimes you don't want a completely random sample. I said, if you have a disease that's 1 in 10,000 and I randomly pick 100 people, it's very likely I'm not going to have anyone with that disease within that sample. So if you're looking for something rare, you don't want a random sample. Now, what happens if I collect more than one sample? Now, most of you filled in the survey to do with height, so it's not really possible for me to ask you to fill in the survey again and get a different sample. But often, when we take multiple samples, we get differences between them. So one sample might be misleading. Multiple samples definitely help us improve our knowledge about the population. But each time you take a sample, you end up with a slightly different mean and a slightly different standard deviation or variance. A good example of this is opinion polls, because you take lots of them in order and you can then compare how they're going. So let's look at an example of some opinion polls. So here are opinion polls before the 2012 US presidential elections. So here you're talking about an election between Obama and Mitt Romney. So at the bottom of the graph you have, bottom of the chart, you have data that was collected on the 19th of the 9th, the 19th of September. Then as you go up the chart, you're getting into October. Now the US elections are always the 3rd of November or the first week in November. So what you see is it going from being strongly blue, where Obama is winning and has a lead of 4% or even up to 9%, to Mitt Romney getting more and more occasions where he's ahead. So from these polls, what it looks like is that Mitt Romney is building electoral momentum to win the election. Now, we know what happened in this election. Obama won by about 5%. So all of that surge of red towards red in those polls turned out to be wrong. And at the time, Mitt Romney called that Mittmentum. So he had the Mittmentum to go to the White House, but he didn't. So why did the polls get it so drastically wrong? Why are the numbers changing, and is there an inherent problem? So if the numbers change, you might actually be seeing a genuine phenomenon, but here we know you're not. So what's gone wrong? Now the simplest thing is bias, and that you've got some incorrect way of collecting your sample, which is causing you to collect the information partially. You're collecting it from more from one side than the other. So what's happening in this particular case? So in this case, a lot of the polls were carried out by phone. Now to do them by phone, you need to have a fixed phone line. Now a fixed phone line biases a certain part of the population. So people who have permanent homes, have lived there for a long period of time and are of a certain age group, are more likely to have a fixed phone line. But they're also more likely to be Republican voters, whereas Democrats are more likely not to have a fixed line because they don't have such long time fixed homes. So this is why they had bias in those particular cases, and there wasn't anything happening that actually changed the properties of the population.